Alright, so a couple of things that we want to address here. And we're going to go back to these rings because there's something very important that we probably didn't mention when we began drawing the structures of the rings, but it's a good time to at least mention them now. And then we're going to look at a reaction of a ring as well. So what I'm going to draw is the Haworth projection of glucose here. So this is going to go down, that one goes up, this one goes down, and we see a CH2OH group here, and then the same thing happens over here, down, up, down, and CH2OH. The difference here is that in this first one, I'm going to put the OH group that goes down, and in this one, I'm going to put the OH group that goes up. Now, we said that this was the alpha form and this was the beta form. And in a previous video, I kind of splurted out some percentages for you to kind of show you that these two rings are basically in solution at the same time. They constantly flip back and forth. They will come to an equilibrium where they constantly change, but they're constantly reforming at the same time, and we get these nice kind of percentages that come from it. And we said that another third percentage here, a very small one, is coming from the straight chain version as well. So if you go back and take a look at that video or look at that slide note, you will see that the beta form was in a higher concentration than the alpha form. And I want to at least take a few seconds to basically address that. You know, how would I have known that the beta form is actually more stable than the alpha form? Well, if you look at these two structures of glucose and you look at the alpha and the beta anomer, well, we've talked about the stability of structures way back in the day. One, we talked about the stability of a six-membered ring, and this is a six-membered ring, and that's good because that leads to stability, which is why the rings are maybe higher percentages than the straight chains, because, you know, you lock them into a ring, they feel comfortable, they feel safe, they feel secure, they know that you're there to take care of them, and they don't really have to hardly worry about anything. So we see these ring structures happen in higher percentages. What about the alpha and the beta? Well, if I look at the alpha, I see an OH group that points down and an OH group that points down. And if I look at the beta version here, a OH points up and an OH points down. So this is kind of a cis notation, and this is almost in a trans notation. And if I look at the structure of glucose, it's for that reason that beta is a higher percentage than the alpha. It's almost coming to you at 3 times the amount, right? So if I look at these two structures, the general rules back in the very first organic class will come back around and give you insight on this stability. And it's basically saying, listen, we've got two OH groups, they are on opposite sides of the ring, and because of that, they are not really conflicting with each other. So they don't like each other, they're like bad neighbors, but at the same time, they're far enough away where they don't tread on each other's property. And that's very good for these OH groups. That's what they want. And because of that, the B is more stable when it concerns the glucose. But that is how you compare stability here. You look at the anomeric carbon, because it's this carbon that's got the choice in changing, right? All the other carbons are locked into place. Those OH groups can't flip. But at that anomeric carbon, we can see some flip that happens. Alpha form and beta form. So you look at the OH group that's beside of it, and you figure out, okay, is this pointed down? If it's the alpha, well, is it on the same side of another OH group? If it is, then that's not going to be the most stable form. If I draw the alpha version down, right, and the next carbon has the OH group that's pointed up, then they are on opposite sides. So the alpha would be kind of stable or more stable in that location. But take a look at these OH groups. Again, compare them. see where they are located, and the transposition will always be the option that's more stable. So for glucose, beta is more stable. Beta is not stable for all the sugars, but for glucose it is, because that is what gives me the trans notation here. All right, so that's one of the take-home things that you should take away from this video. Number one is how to predict stability. Number two, though, is I need to look at this structure, and I need to understand that there's reactivity that can happen with these rings as well. And the reactivity can happen again at these OH groups. So this OH group on the glucose structure itself has reactivity. And these things can react with an alcohol. So either one of these, it doesn't really matter, but either one of these can react with an alcohol. And we can get a product. So let's just pick a random alcohol. Let's do ethanol, CH3CH2OH, and it needs a little bit of acid in order to go forward. Now this is not a new reaction for you. It shouldn't be, at least, because look at it. It's an OH group. We are putting it into an acidic environment, so we are protonating that OH group. That makes it a very good leaving group. If we can have maybe a stronger nucleophile to come in to kick that protonated OH group off, then we can get a substitution to happen. And that's exactly what goes on here. So when I take these sugars and I react them with ethanol or an alcohol, methanol, ethanol, isopropyl alcohol, it doesn't matter. But when I take these sugars and I react them with an alcohol, I get a new product that forms. And what happens here is just a true blue substitution reaction. This OH group is going to be substituted for the OCH2CH3 group, and then everything else stays the same in the molecule. It doesn't really get touched at all. So this is what we see happen with the actual sugar itself. So if I take a ring structure and it has this OH group on it, this OH group, well, that's a little different because its neighbor is another oxygen, right? So that OH group is susceptible to attack. I put the hydrogen in it, protonate it, make it ugly, so therefore another pretty nucleophile can come in and switch places with it, and that's exactly what it does. We call this new type of structure here a glycoside. So Glycoside. We call it a glycoside. The bond that happens between the carbon and the oxygen of that group, so this bond that connects the C and the O together, that's called a glycosidic bond. So we make a glycoside, and that makes a glycosidic bond. Now this is a 6-membered ring, so we could actually call this a pyranoside if we wanted. If it was a 5-membered ring, we could call it a furanoside if we wanted. But this is a glycoside. It forms a glycosidic bond. That is the bond again that we call between carbon and oxygen. And we can go on a little further, and depending on the number of carbons in the ring, we can call it pyranosides or furanosides. So it's up to you on how you want to label it, but that's some more terminology and one more reaction that we can throw in to basically talk about these carbohydrate chemistries. Okay, so mechanism, we're not going to talk about it. This is something that you've probably have seen before. Just go back and review the text. You won't see it on the test. You won't see it on the quizzes. You might see it in the homework, but again, you've got the textbook for the homework, and you don't have to complete it as soon as you open it. So we treat that a little bit differently. We can go a little bit more in depth there, but as far as testing purposes go, the answer is no. Okay, so next video, we are going to be looking at what we would call a reducing sugar. So there's certain sugars out there that reduce, and there's certain sugars that do not reduce. We call those non-reducing. Imagine that. So reducing and non-reducing sugars we will look at in the next 10 minutes.